Two separate light exposures, printed side by side on silicon. No gap, no seam you can use. Here is exactly how they become one working chip, aligned to a few nanometers. Here's the wall. One shot from an EUV machine can only print a rectangle about 26 by 33 millimeters. That is the biggest area a single exposure covers. But the hungriest AI chips want to be larger than that, right up near 800 square millimeters and beyond. So chip size hits a hard limit set by the optics, not by the design. Unless you cheat. Start with the stencil. Every chip pattern lives on a flat plate the machine copies onto the wafer. That plate is the photomask, also called a reticle, a quartz sheet with the circuit pattern laid out in a material that blocks light. The scanner shines light through the pattern and projects it down. Simple enough. But EUV breaks the old rules. EUV light has a wavelength of just 13.5 nanometers, and here's the catch. Everything absorbs it. Glass, air, even the mask itself. You can't shine it through anything. So an EUV mask doesn't work by transmission. It works by reflection. The pattern sits on a mirror. Dozens of ultra-thin layers of molybdenum and silicon stacked to bounce that 13.5 nanometer light back up. On top of the mirror, an absorber blocks light where you don't want circuit. One more trick. The pattern on the mask is 4 times bigger than what lands on the wafer. The scanner's lenses shrink it 4-fold on the way down. Why bother? Because making tiny features on a big mask is far easier than making them on the chip directly. One mask holds one field. The machine prints it, shifts over, prints it again, step and repeat across the whole wafer. Now the cheat. If one mask only covers one field and your chip is too big for one field, split it. This is reticle stitching. You take the oversized design and cut it into 2 halves, each small enough to fit inside a field. Each half gets its own mask. The machine prints the first half, then prints the second half right next to it, edge to edge on the same silicon. 2 exposures, 1 chip. But you can't just chop a chip anywhere. Slice through a dense block of transistors and you'll destroy thousands of connections. So the cut follows a stitch line placed where the circuit is thin, usually in the wiring between blocks, not the packed logic itself. Fewer things to reconnect there. And the edges have to meet perfectly. Designers draw the features near the seam so the 2 exposures either overlap slightly or butt cleanly together. No gap that leaves a wire dangling, no overrun that shorts 2 wires into one. The seam is engineered, not accidental. Which raises the real problem. Printing 2 fields is easy. Landing the second one exactly on the first. That is where nanometers decide whether the chip lives. So how good does the aim have to be? Brutal. Field 2 has to land on field 1 within a few nanometers. For scale, a single transistor gate today is smaller than 10 nanometers across, and the seam has to align tighter than that. Miss by a hair and the wires on each side don't touch. You get an open circuit, a dead chip. Here's how the machine hits it. First, the wafer carries tiny alignment marks etched into the silicon. Reference points the scanner reads to know exactly where it is. Second, the stage that moves the wafer is tracked by laser interferometry. It bounces laser light off the moving stage and counts the wavelengths to measure position down to fractions of a nanometer. That combination tells the machine where field 1 landed, so it can place field 2 right on top of the edge. This precision, how well one layer sits on another, is called overlay. And the overlay budget at the seam is savage. A few nanometers is the entire difference between a connected wire and a broken one. One more advantage. Both fields print on the same wafer in the same machine back to back, seconds apart. Nothing has time to shift or drift. The seam matches because nothing moved between the 2 shots. So why doesn't everyone do this? Because it's expensive on 2 fronts. First time, every stitch die needs 2 exposures instead of 1, so the machine spends roughly twice as long per chip. EUV scanner time is some of the most costly manufacturing time on Earth. Doubling it doubles the bill. Second, yield. A normal chip has 1 shot to go wrong. A stitch chip has that plus the seam. Any defect right at the join or an overlay miss of a few nanometers and the whole die dies. 2 fields mean 2 chances to fail plus the risky seam between them. So a stitch chip is harder to make good and fewer come out working. Put those together and stitching only pays off when the chip simply cannot fit any other way. That's why it's reserved for the giants. Wafer-scale AI engines the size of a dinner plate, the biggest GPUs and large camera image sensors. For those, no single 26 by 33 millimeter field is big enough. So the extra cost is the only path to the size the design demands. So here's the whole trick in one motion. You take a chip too big for the machine's 26 by 33 millimeter window. You cut it along a stitch line where the wiring is thin, so few connections cross the cut. Each half becomes its own mask. You print them side by side on the same wafer in the same machine back to back. And you land the second field on the first within a few nanometers. That nanometer scale overlay is the entire game. Get it right and a wire can run straight across the seam as if the split never happened. The circuit crosses the join intact. The two fields stop being two fields and become one die. And that is how a chip escapes the optical limit that used to cap its size. The 5 nanometer class alignment at the seam is what turns two separate exposures into a single working chip. And it's exactly what lets today's largest AI silicon exist at all. So that's wafer stitching. Two EUV fields joined at an engineered seam aligned to a few nanometers, printed into one die bigger than any single shot allows. But two fields is just the start. What happens when you stitch dozens of fields across an entire wafer and treat the whole disk as one enormous chip? That's true wafer-scale integration, and it changes everything about how a computer is built. That's next.